This is a lecture about molecular orbital theory. Molecular orbital theory and valence bond theory. Now, valence bond theory uses hybridization of atomic orbitals to explain bonding and formation of molecules, and it's an alternative to the molecular orbital theory. So, valence bond theory came first, so we're going to talk about the reasons that molecular orbital theory might be better than valence bond theory. One of the most important is that the valence bond theory is not able to explain that substances are magnetic. You may have done the experiment where you have different salts or substances and you put them on an electronic balance, and some of them weigh more than they should or less than they should. And that is due to some of them having a magnetic field. And it turns out, of course, anything that has a charge emanates a magnetic field. And so in a compound, if we have unpaired electrons, there's a net magnetic field. And if we have paired electrons, if all of the electrons in a compound are paired, each of these electrons creates a magnetic field, but it's exactly canceled out by the electron it's paired with. So if all the electrons are paired, the substance is called diamagnetic, and it won't have a magnetic field. And if we have any unpaired electrons at all, the substance will be called paramagnetic. And the molecular orbital theory explains that very well. Valence bond theory and Lewis theory do not. So if we look back for a minute at the Lewis diagram of molecular oxygen, O2, looks like everything's paired up real nicely. Okay, and that's what people thought back in the time. Okay, all the electrons are paired. It should not have magnetic properties. But lo and behold, it turns out that molecular oxygen is actually paramagnetic. There are unpaired electrons. And the Lewis theory, as well as valence bond theory, did not predict that. If you look at the orbital diagram for two oxygen atoms, you can see that they each have two unpaired electrons. But if we put these together, okay, if we make a bond between two oxygen atoms, it looks like everything's going to be paired up really nicely. So just to kind of reiterate, the valence bond theory and Lewis theory are not able to explain why molecular oxygen is paramagnetic. A second primary reason why valence bond theory falls short is valence bond theory starts with atomic orbitals like S and P, for example, and says that they form hybrids, so just say SP orbitals, but these hybrids then are still localized between the two atoms that are bonding. Okay, so the bottom line is in valence bond theory, the orbitals that are used to bond between atoms are still localized between the two atoms that are bonding. Okay, and because of that, we have a hard time explaining delocalization. You may remember when we were drawing Lewis structures that sometimes we had to draw equivalent Lewis structures to show resonance. And ozone is a real good example of that. In order to accurately represent ozone, we have to draw both of these resonance structures because the two electrons that are in this pi bond are shared between the two sites, okay? And we have to show that. Well, valence bond theory doesn't really account for that because the hybrid orbitals formed, again, are localized between the two atoms bonding. And so there's no way to really account for sharing of pi electrons. However, you will see that in molecular orbital theory, the theory goes that atomic orbitals like S and P, for example, combine to give us delocalize molecular orbitals. What do I mean by that? So the molecular orbitals that are formed according to molecular orbital theory are delocalized throughout the entire compound, okay, rather than only in between the two atoms that are bonding. And that allows for sharing of any of the valence electrons in the pi bonding system anyway, among all the atoms that are involved in that pi bonding system. All right, so just kind of a summary of the molecular orbital approach. You may remember that an orbital, it results from Schrodinger's wave equations, and that the solution, the mathematical solution to his wave equations, give us the shapes of the atomic orbitals, okay? And that, remember, is a region of space in which we are likely to find an electron. Well, because these orbitals are essentially wave functions, you may remember from physics that waves can be added together in a constructive fashion, like if they're in phase, to kind of accentuate the wave. And in the case of molecular orbital theory, if they're added constructively, they give a lower energy, more stable molecular orbital. And wave functions can also be added together destructively out of phase, which gives a higher energy, less stable molecular orbital. So let's look at a diagram of that. So let's say that we have two atomic orbitals of substances that are bonding together. Let's say they're each coming with a p atomic orbital, each with one electron. Okay, what molecular orbital theory says is that the atomic orbitals will combine constructively to give us a bonding molecular orbital that's lower in energy and more stable, and will also combine destructively to give us a higher energy, less stable anti-bonding molecular orbital. Remember the conservation of orbitals. In other words, the number of atomic orbitals that you start with, okay, must equal the number of molecular orbitals you end up with. Okay, that's true for both valence bond theory and molecular orbital theory. So the bottom line is, if we distribute electrons in the molecular orbitals when atoms are bonding, if we end up with a net surplus of electrons in these lower energy, more stable bonding molecular orbitals, that suggests that a bond will be made between those atoms. If, on the other hand, we end up with too many electrons in an anti-bonding, higher energy molecular orbital, that does not suggest that those two atoms will form a bond. So that's worth jotting down and remembering. This is just a really nice summary table. I found it online of the key differences between valence bond theory and molecular orbital theory. It's kind of a favorite type of exam question to ask. So you should know at least the first couple of points. And again, valence bond theory considers bonds made as localized between the atoms that are bonding. And the molecular orbital theory considers the molecular orbitals, the new orbitals formed, to be delocalized or spread throughout the entire molecule. Valence bond theory, remember, both valence bond and molecular consider that atomic orbitals are overlapping, but valence bond theory says that atomic orbitals overlap to give hybrids, sp, sp2, sp3. And molecular orbital theory says atomic orbitals overlap to form molecular orbitals. You'll see in the charts we have later that the molecular orbitals are given names like this, sigma and pi, and these asterisks have a significance, which I'll explain later too. I think those are by far the two most important ones to be aware of. All right, so here is a more complex molecular orbital diagram. I want to point out a couple things. On the left and right sides of a molecular orbital diagram represent the atomic orbitals for each of the atoms that are bonding. Okay? So let's just say you want to see how nitrogen bonds with another nitrogen atom. So you would put one atom that's bonding on each side, and you would fill up the electrons. We know that each nitrogen has, it's in group 5A, so each nitrogen has 5 valence electrons. So we're going to go ahead and fill those in. Make sure you follow Aufbau's rule and Hund's rule and Pauli exclusion. All right, so this is how we show the unbonded atoms on the left and right side, and I'll be showing you how to transfer those valence electrons to the molecular orbitals in the middle. There are different molecular orbital diagrams, primarily in this drawing. Hopefully you can see that the ordering of the sigma and pi orbitals in the middle are different, and that depends on the atoms that are bonding. I'm not going to go into details here, but oxygen and fluorine are on the right-hand side of period 2 in the periodic table. So their P sub level is more than half full, okay? And then the others, boron, carbon, nitrogen, are to the left of period 2 in the periodic table, and their P sub levels are less than or equal to half full, okay? So that ends up affecting interaction between S and P orbitals and flips the relative energy levels, which you don't need to know at this point. But I do want you to know there are different molecular orbital diagrams, and at least for my class, I will be giving you the correct diagram to use. You just need to learn how to place valence electrons into it. Alrighty, so as I said before, the atoms that are bonding are shown on the left and right of the diagram with the number of valence electrons they have. In this case, we're looking to see if 2 lithium atoms might form a bond. Lithium's in group 1A, so each of the lithium atoms has 1 valence electron. So really, it's quite simple. All you do is count the total number of valence electrons. In this case, you have 2. And place all of the valence electrons into the molecular orbitals in the center of the diagram, making sure you follow Aufbau principle, Hund's rule, Pauli exclusion. So I have a total of 2 valence electrons I need to place in the middle. 1, 2. Okay, that's it. We're done. We've used all the electrons up. So we have a net bonding situation. You see how all the valence electrons ended up in a lower energy bonding orbital, which is energetically very favorable, which means that the lithium-lithium bond can in fact and does in fact form because it's favorable, energetically favorable. Not all of them are. Let's look at one of the frequent questions you'll be asked is to determine the bond order between 2 atoms using a molecular orbital diagram. It's really very simple. There is a formula for bond order, but before we talk about that, I want to point out very simply, bond order is just how many bonds are between 2 atoms. So if there's a single bond between 2 atoms, the bond order is 1. If there's a double bond, the bond order is 2. If there's a triple bond, the bond order is 3. It's that simple. Okay, so if you're looking at a molecular orbital diagram and you're trying to determine the bond order, based on the diagram, you'll use this formula. So it is the number of electrons in bonding molecular orbitals minus the number of electrons in anti-bonding molecular orbitals, all divided by 2. So let's do some of those. All right, let's say that we wanted to figure out whether helium bonding with another helium is energetically favorable. So we go ahead and set up our molecular orbital diagram. Helium has 2 valence electrons, so each of the helium atom has 2. So altogether now, 2 plus 2, we have 4 valence electrons. So we need to place all of those 4 valence electrons in the center molecular orbitals. So 1, 2, 3, 4. And now we're done. So let's go ahead and figure out the bonding order according to that formula. So it was the number of bonding electrons and bonding orbitals. So that's 2. All the orbitals of lower energy from where they started are bonding. So that's 2 electrons in bonding orbitals. How many electrons do we have in antibonding? Antibonding is any orbital that's higher in energy than what it started from. Another thing is that antibonding orbitals have asterisks next to their symbol, meaning they're antibonding. So there are 2 electrons in antibonding orbital. Divide that all by 2, and we get that the bond order for a helium-helium bond is 0. What on earth does that mean to have a 0 bond order? That means no bond forms, okay? So you can pretty much see that intuitively too. If you look at this diagram, if bonding electrons and anti-bonding electrons exactly cancel each other out, there's going to be no bond, okay? There's going to be a bond order of 0. So let's look at 2 atoms that actually make a bond. At the helium-2 plus 1. So remember that plus sign means that you have lost 1 electron. Okay, so it doesn't matter which helium atom you want to lose the electron. Just make one of them have 1 valence instead of 2. So now you have a total of 3 valence that you need to place in the middle, molecular orbitals. So it's 1, 2, 3. Now, hopefully, you can see that you have a net bonding electrons. But let's go ahead and fill in the formula. We have 2 electrons in bonding molecular orbitals, and now only 1 electron in the anti-bonding orbital. So using our formula for bond order, find the bond order is 1/2. So yes, helium-helium can form a bond. There's a net drive, maybe not as strong of a drive as making a whole single or double or triple bond, but there's still some amount of bond formation and at least 1 electron shared between them. All right, this is cool. I love this diagram. This is how the molecular orbital theory explains the paramagnetism of molecular oxygen, O2. So oxygen, being in group 6A, each oxygen atom has 6 valence electrons. Okay, so this is what their atomic orbital diagrams look like. Now, most importantly, though, is how many total valence electrons do we have? We have 12, 6 plus 2. And those 12 valence electrons need to be placed in the middle molecular orbitals so that we can determine whether or not it'll bond in the bond order. So again, follow Aufbau and Hund's rule and Pauli exclusion. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alrighty, so that is the 12 valence electrons placed for molecular oxygen. So let's find the bond order first, okay? So how many electrons are in bonding molecular orbitals? Let's see, 2, 4, 6, 8. How many electrons are in anti-bonding orbitals? 2, 3, 4. Okay, so the difference in those divided by 2 gives you a bond order of 2, which means, according to theory, molecular oxygen should have a double bond. And it does. So it supports that beautifully. Okay, now we need to determine whether oxygen is paramagnetic or diamagnetic. Now, because we have to find Hund's rule, these last 2 electrons go into unpaired equal energy p sublevel, and so we find finally a theory that explains that molecular oxygen is paramagnetic. In other words, it has unpaired electrons. Alrighty, just another quick example. Let's see, we wanted to demonstrate or support that fluorine can make a bond with another fluorine. Alrighty, so each of the fluorines has 7 valence electrons. So we have a total of 14 valence electrons to place in the middle. So 2, 4, 6, 8, 10, 12, 14. Okay, so what would the bond order be? How many do we have in bonding orbitals? 2, 4, 6, 8. How many in anti-bonding orbitals? 2, 4, 6. Something's not right there. Whoops, why did I divide by 4? That's bizarre. Okay. So the bond order is 1, which means that when fluorine bonds with another fluorine, there should be a single bond or bond order of 1 between them. And that's actually true. That actually is the case with molecular fluorine. All right, so here's a couple for you to try on your own. Here's one of them, but I would go ahead and shut off the lecture. See if you can figure out this one and the one on the next page before I explain. All right, I'm hoping you tried this on your own. So on one side of the molecular orbital diagram is going to be nitrogen and oxygen on the other side. Doesn't matter what side goes where. Nitrogen's in group 5A, so it has 5 valence electrons. Oxygen is in group 6A, so it has 6 valence electrons. Alrighty. So now you need to count total number of valence electrons and place all of those in the center. So 1, 2, 3, 4. We have 5 on the left side and 4, 5, 6 on the right side. Actually, you didn't even, unless you're asked, you don't need to fill in these atomic orbitals. Just memorize the how many. How did I do that? How many valence electrons every atom has? Okay, that. Nitrogen has 5 and oxygen has 6, so you have total 11 valence electrons, and then start filling them in, following the rules. So we have 2, 4, 6, 8, 10, 11. Okay, so nitrogen monoxide has a bond order of, let's see, how many do we have in bonding MOs? We have 2, 4, 6, 8. How many do we have in anti-bonding MOs? 2, 3. All right, so the bond order for nitrogen dioxide is 2.5. If you were to draw out a Lewis structure, that half, the fact that it's half and not just 2, there is an unpaired electron that can bounce back and forth between nitrogen and oxygen. So that's it for molecular orbital theory. I do have a lecture on valence bond theory too, if you'd like to listen to that.